Hello, welcome. Let's talk about physics. So we're almost done with 2D motion. Most of 2D motion, for the last lesson, we said we have a velocity that's angled. If we have a velocity at some angle, we can break the velocity vector into x and y. But let's talk about the reverse. What if we have two velocities and we want to add them, add the vectors together to get one sum or resultant? This makes sense for displacement. If I'm following a treasure map and it says walk 10 meters north and then 2 meters west, I walk one displacement, I stop, and then I do another displacement. My total displacement is the vector sum of those displacements. Does it make sense for velocities? I may have given some hints. You may have seen some examples already in practice problems, but when would you add two velocity vectors? Tell me right now if you know. When do you add two velocity vectors? Okay, here, I'll show you.
He's nearly here. He's not nearly here.
Come on! You can do it!
Man.
Come on!
You can do it, bro.
Go, go, go! Run!
Believe
Run!
in you.
Oh dear! Oh fuck!
Okay, great video. I liked how the guy just kind of steps over him at the end. That's pretty good. So what happened? What velocities were there in that video? Let's talk about it. There was a guy on the escalator. Let's call him person A. He was walking down the escalator at some speed. There was a camera person at the bottom recording him. Ooh, time to draw a great camera. That's what cameras look like. Perfect. Let's call them C for camera. And finally, let's pretend there's an invisible person B right behind person A who's standing still. Person B, because they weren't really there, but they were not moving. A stationary person, person B, watching person A. And person B and person A are on the escalator going up. Let's call up the positive direction. It's not really up, it's kind of like up and right, but we can make anything up or positive. So this way is positive, this way would be negative in this problem. Let's say this person was walking down. Let's say person A and person B are heavily inebriated. So they're so intoxicated, they don't realize they're on an escalator. They think they're on stairs. Just go with it. It's fine. They think they're on stairs. So person B thinks they're standing on the stairs, stationary, and person A thinks they're walking 2 meters per second down the stairs. But what actually happened is they're not on stairs, they're on an escalator, and the escalator is going 2 meters per second upward. It might be a little fast for an escalator, but go with it. And person C is watching person A. Before person A hopped on the middle of the escalators and started sliding, were they moving? Were they moving? This is a very silly question, but whatever. Was person A moving in the first half of the video? There are two answers to this problem, and they're both correct. Person A was moving at 2 meters per second relative to person B. But person A was not moving at all, or moving 0 meters per second, relative to person C. Both are correct. We can write those velocities two ways. The velocity of person A relative to person B, and the velocity of person A relative to person C. They are not the same. If up is the positive direction, B is intoxicated, and they're looking at A, and they see A getting 2 meters per second farther from them. They're getting 2 meters farther from them every second. Every second, person A is 2 meters down the stairs from person B. So velocity of A relative to B is negative 2 meters per second. Person A relative to person C is not moving. In the first half of the video, the camera person is recording person A, and it looks like they're not moving. We know there's escalator stuff going on, but pretend they were in an altered state of mind and didn't realize what was happening. These are not equal, but there's a very simple relationship between them. The velocity of person A relative to person C, oh, that's the name of this lesson, by the way, relative velocity. The velocity of A relative to C is the velocity of A relative to B plus the velocity of B relative to C, as long as they're all vector sums. How fast was B going relative to C? Well, if B is standing on the escalator and C looks up at B, C will see B going up at 2 meters per second. The vector sum of negative, what if I n%? The vector sum of negative 2 and positive 2 meters per second is 0. So it does check out. The velocity of A relative to C is the velocity of A relative to B plus the velocity of B relative to C. This isn't really like a mathematical rule, but you can kind of say, oh, the B's in the middle cancel out. So it's A relative to C once the B's disappear in your vector sum. As long as you remember they're vectors and you think about the direction and how it affects the number, you're fine. It's good. This works in a one-dimensional problem like this, but also two-dimensional, which we'll see real soon. But let's see an example of this really fast. Yeah, watch this video. So in this video, there's a truck that drives 50 miles an hour. No, I'm not going to give it away. There's a truck that drives 50 miles an hour, and there's a cannon that shoots a ball also 50 miles an hour. What would happen if the cannon were shot backwards from the truck? What if you shoot a cannon 50 miles an hour backwards off a truck moving 50 miles an hour forward? Let's see. The ball just drops straight down. It's like the ball just kind of falls vertically. The horizontal motion cancels out. If you look from the truck's perspective, the ball is shot backwards, right there. Relative to the truck, the ball does get launched backward. But relative to the ground, relative to the camera, relative to a stationary observer, it just drops vertically with 0 initial velocity. Because its vector resultant velocity is the velocity of the cannon plus the velocity of the truck. Or to be specific, it's the velocity of the cannon relative to the truck plus the velocity of the truck relative to the ground, which is 0. So there's an example of that. Relative velocity. That was a 1D motion problem. We're talking about vectors, so it works for 2D also. The most common example of this is a river. Alright, let's say we got a river. And the river flows, oh, I don't know, 3 meters per second. And another word for the direction the river's flowing is downstream, and this is upstream. This isn't like a vertical river, like a waterfall. But when I say upstream, I mean this way. When I say downstream, I mean this way, in case you've never heard those terms before. So let's say there's a swimmer in the water. That's what swimmers look like. And they want to swim straight across the river to get to the other side. And normally in the pool, in a pond, in still water, this person, maybe their name is Nick, can swim 4 meters per second. Is this a scale vector? No. Pretty fast? Yeah, probably. Don't worry about it. While they're swimming, their swimming coach, whose name I guess is Coach, is watching. And they're saying, go, 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 swim, 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 do it. So we have 2 velocities. This is the velocity of Nick relative to the river. This is the velocity of the river relative to Coach. And the velocity of the coach is 0. Yeah, that makes sense to me. Seems fine. Okay. If the swimmer, Nick, looks straight across the river and says, I'm going to swim that way, and then just starts swimming that way, will they reach the point across the river horizontally? What do you think? Will Nick swim? Will Nick reach this point if he swims straight at that point through the moving water? Well, if he's swimming this way through the water, but the water is moving, his actual velocity is not 4 meters per second. He'll have this velocity, 4 meters per second, plus this velocity, 3 meters per second. He'll have this resultant velocity. Oh wow, it ends up being 5 meters per second. The numbers worked out nicely. Who could bring it to that? The coach will say, oh, your velocity is your velocity relative to the river plus the river's velocity relative to me. So even though Nick intends to swim horizontally, he's going to be moving diagonally because of the river's velocity too. Okay, that makes sense. How could Nick actually swim across the river? Assume he can. If the river was super strong and super fast, he wouldn't be able to. But let's say he's a really good swimmer and the river's not going that fast, which is not with these numbers, it's fine. How can he swim to actually get across horizontally? What should he do? Tell me right now. What does he do to actually swim across the river? I'm going to erase this. This is not the answer. I'm going to redraw it over here. Okay. So he wants his actual velocity, or his velocity relative to someone stationary, like his coach. He wants his total velocity, v Nick relative to coach, to be horizontal. Remember, how do you find a resultant velocity of Nick relative to coach? It's the velocity of what are we talking about? Oh yeah, Nick relative to the river plus the velocity of the river relative to the coach. This is still 4 meters per second. He's still swimming the same speed through the water. He's still swimming 4 meters per second. But if he wants to go straight across the river, he can't swim. He can't aim himself straight across. He has to aim himself diagonally like this. He'll swim this way, then the water will push him down. Then he'll swim this way, and the water will push him down. Then he'll swim this way, and the water will push him down. So he'll actually be going horizontally, even though he's trying to swim diagonally. If this is 4 meters per second, and this is 3 meters per second, this resultant will not be 5. It'll be square root 7 meters per second. Please never give me answers like this. I'm just too lazy to solve it. Square root 7 meters per second. Hopefully you... Let's put that in there. This is not the same triangle as this. And this angle, theta 1, is not the same as this, theta 2. These are not the same triangle. They're both right triangles. That's all they have in common besides that. Because the swimmer has to use part of their velocity to cancel or counteract the river's velocity, they're going to swim much slower than they would normally. This is less than 4 meters per second. Yeah. So, yeah. If you want to swim across the river and ignore the river's current, you have to swim at some angled velocity vector, v, where one component, the vy of your velocity, would be 3 meters per second. So obviously, if you want to get across the river, you're not going to swim straight up against the river's currents. But if you swim such that the y component of your velocity is 3 meters per second upstream, this y component plus this 3 meters per second downstream component of the river's velocity will give you a resultant that's horizontal. So there you guys go. This works for any velocity vectors in relative motion. They don't have to be right angles at all. In fact, you can have no right angles in the problem, which would be quite a spicy problem. If you are a pirate, and you read your treasure map and it says, go sail 100, go sail 20, go sail 12 meters per second at an angle 35 degrees north of east. But while you're sailing, there's some strong ocean currents that are going 20 meters per second at an angle negative 70 degrees. This is the velocity of your boat relative to the water. But this is the velocity of the water relative to a stationary object. Then your total velocity, the velocity of the boat relative to a stationary object, is the vector sum velocity boat to water plus velocity of water to stationary is the velocity of the boat relative to stationary. None of them are orthogonal, so you'd have to do a lot of trig to solve this problem. But it is doable. And if you want to do some shortcuts, you do some law of sines, law of cosines, which I'm not even going to talk about, because that's way too hard for me. So one last example before we end the video. What would happen if you shoot a ball vertically out of a car moving horizontally? So pretty famous physics demonstration. There's a little cart with a cannon on top. It'll be shot straight up while the cart's moving. Physics is not real life. It's an ideal situation. If there's no air resistance and no wind or anything like that, yeah, the ball is shot straight up and it lands right back down in the cart. For us, it's a 2D motion problem. The ball is shot diagonally. It has some initial horizontal velocity and some initial vertical velocity. But the horizontal velocity is from the cart. So relative to us, it moves diagonally. Relative to the cart, it's just a vertical problem. Relative to the cart, the ball goes straight up and straight back down and lands right where it started. Not relative to us, relative to the cart. So that's an example. That's the lesson. Do some practice. I'll talk to you guys soon.